fatigue. So before I just start off the topic, I just want everyone to think about the daily life fatigue you can think about. For example, give you a hint, a human body, if you're running for a marathon, what's happening? So you feel very painful at your knees. So basically you are applying some fatigue stress on your bones. So you feel very uncomfortable after probably 1,000 times fatigue load. Okay, so remember this graph. We're talking about there's a various of failure. We have finished plasticity and also cracking. And now we are moving to the fatigue failure, which most of the time for the brittle material, and it takes probably years to finally reach the fatigue failure. So it's basically a lifetime of a material. So actually, fatigue, if you look at all the engineering failure, they're accounting for 80 to 90% of this disaster or failure. And most of the time is polymer and ceramics. They are very vulnerable to the fatigue. And actually, Dr. Frank from Queen Mary, from our university, was the first to demonstrate the genuine mechanical fatigue in ceramic. So that's good. Actually, the theory most of the time is developed here. And we are kind of carry the history, and we want to just to let everyone to know the basic knowledge in this lecture. So for the fatigue failure, you can see they have caused various disasters. For example, for this aircraft wing. So instead of failure on other place, most of the wing part, if you think when the wing is flying, so this is the joint between the wing and the fuselage. So the wing is changing all the time, depending on wind, right? And they generate a lot of fatigue stress on that area. And eventually there will some kind of fatigue crack initiated and suddenly leading to this kind of disaster. And some also things, you probably take a lot of either tube or train to London, and every place they were using all kind of rail here, most of the time made of steel. Imagine the train actually look at the rolling contact between the wheel and the rail. So basically you keep applying that rolling contact stress on the rail. So eventually it will lead to some fatigue failure like this crack. So this is kind of 2000 failure, and basically takes a lot of time to repair these kind of things. And another type of failure, common failure happens, for example, this rally car suspension. So basically you have so many extreme loading happens on the car, and you can feel the shaking of your car when you're driving such a wild environment. And so the suspension is keep doing this fatigue stress. Eventually there's some failure here like this. And also some like span when you're doing that to unscrew or screw a bolt, they will eventually leading to some failure. But it takes several years to break a spanner, I guess. You need to do very hard. Okay? So take a look at the picture here. Is just give you the classification of different fatigue failure. So one typical one is the cyclic fatigue. So basically you have a cyclic load or fluctuating load. Or sometimes is the static fatigue. You apply constant loading, or you have some stress, corrosion, cracking. But in this lecture or this module, we most of the time just focus on the cyclic fatigue. Okay? And cyclic fatigue can be further divided into several groups. For the uncracked substructure or structure, basically there's no crack you can observe at the beginning, so it's a pristine structure. So we are talking about how to generate the crack or initiate the crack using fatigue load. Or if there is a crack already there, like a pre-crack, the fatigue load will actually force the crack to propagate. So that's the second group. So we are talking about both. So in the lecture, we will go through this first part. Firstly, go through this part. So for this type of fatigue, actually, you have something called low cycle fatigue, which actually means your cycle life is very short, very low. So that means your structure fail very early, just because you apply a stress close to the yield strength. So that type of stress is really high, so even higher than your yield strength. So basically, you are failure that by reaching the yielding point. So that's why you have less cycle numbers. But in comparison or by contrast here, if you apply a very tiny load, like for example 10% of your yield strength, and you will reach a very high cycle number. So it takes probably years to failure a sample. Okay? So there's 3 stages of fatigue. First of all, you need to actually have the crack initiation. So that's part of the crack nucleation. So there's some imperfection inside the material. So some a void. Eventually, they will connect to a crack and nucleate this crack. And once the crack has initiated, and there's some like slow crack growth region, and finally, it will have a fast crack, which we normally call the brittle failure. And you cannot stop it. So each stage has a different importance depending on the category of fatigue. So fatigue basically is all about cracks. So in this part, we first of all look at the crack nucleation. But before I do that, let's just look at the typical failure, which I have shown you in the first introduction. This is for a bolt from your bicycle, actually, on the probably behind, just on the bottom of the seat, actually. This kind of bolt is, if you look at the fracture surface, so there is an initiation at the crack tip here. So after a certain amount of fatigue load, you can see some slow fatigue crack growth at this region. So you can see the crack surface is very different from either here or the final part, this part. And once you reach the critical stress intensity factor, basically you have a much more like a brittle failure. So after that is a fast fracture, probably bang, and then you just get a completely 2 pieces of material. Okay? And so let's look at the cyclic fatigue. Basically, you're applying kind of a waveform of stress on your material. But this waveform, for example, here is a sine wave or cosine wave. You need to look at different numbers here. So we are plotting the stress against the time. So if you just look at one cycle, it's just one period of this load. And there's several things you need to look at. First of all is the range of your stress, which is delta sigma. So I would encourage everyone just to draw it, because there's a lot of basic values or variables you need to remember here. So I will do it on the paper. Okay? So look at we are plotting stress and against time. Okay? And now it's follow this kind of waveform. It's a sine wave. Let's just look at probably one period here. Okay? And there's a dashed line which basically crosses to the middle of this curve. This is called mean stress. So basically the average of the stress, especially the maximum here. Okay? Sigma maximum. And there's a smallest value, sigma mean. Right? And if you look at the gap between sigma max and sigma mean, which is delta sigma, which is equal to sigma max minus sigma mean. So that's the range of your stress. Okay? So let's say stress variables, including, first of all, the range, stress range. What else is the mean, which is the sigma mean I draw here. It's half of the maximum stress plus minimum stress. Okay? And then there's an amplitude, which is sigma A. So amplitude basically is just from the mean to your maximum, or from the mean to your minimum. So they are kind of amplitude. So that is half of sigma max minus sigma mean. Okay? And one final variables you need to remember, which is the stress ratio. Stress ratio is the ratio between sigma mean over sigma max. Okay? So let's look at some example later on to further understand what's the meaning of these variables. Okay? So in this kind of case, you need to think about, we will talk about the example for the curve later. And let's go back to the slides. Okay? So these variables in the cyclic fatigue loading. Okay? Another things, we are plotting the stress against time, but also there's things to measure the lifetime, which is the number of stress cycles leading to the final failure, which is n. Okay, you can put a F here. It means the number of cycles to failure. And if you divide the number over time, give you the frequency. So basically, for a typical fatigue problem, there's two parts. Crack nucleation, that takes several, probably hundred of cycles, and plus some crack propagation due to the fatigue load, which is the propagation fatigue number. You plus these two numbers, give you the final number of cycles to failure. Okay? So now we look at the typical example for this stress time profiles. Okay? So look at the one. So basically, just look at the one which is most representative, r equal to -1. What that means is your sigma max equal to sigma mean, but they are in a different sign. So that means this sigma r means the sigma mean over sigma max, right? That gives you the -1. Understand? So this is just the a typical example for the loading you can apply on the sample. So let's just look at the example first, this one. So sigma max here, sigma mean. Now if you look at the sigma average stress, sigma m equal to 0, right? But if you look at the stress ratio, which is sigma mean over sigma max, basically, if you give a number here, here is minus r, minus sigma, here equal to sigma. So that gives you minus sigma over sigma. So that gives you the value minus 1. Okay? It looks a bit weird, but if you get familiar with that, that every time you look at r equal to minus 1, okay, that is the typical loading where the mean stress is 0. So what happens if you shift the curve? Again, this time, this is the stress. So you shift all the curve up to somewhere above the horizontal axis. Now your sigma mean is here. And now you look at the sigma minimum, sigma maximum. Let's say here is around sigma, okay? Here around 3 sigma, just to give an example. So sigma mean, sigma max now equal to over 3 sigma. That's a third. That just tell you, if you shift that up, then the stress ratio is larger than 0. Similarly, there's some other case. When you just shift it such that the minimum stress, okay, equal to 0, the sigma mean, minimum, sigma max, okay? So R equal to sigma mean, minimum, max. Now it's 0 over any value you put. So that is sigma equal to 0. So likewise, if you shift the whole curve in the bottom, okay? So everyone can see that? Now you will get definitely, they are both negative. For example, this is a sigma minus 3, and this is minus sigma. Now let's look at the minimum value, which is 3 sigma. Maximum value is this, so about 3, okay? So it's changing, depends on where you put your stress curve, okay? What you need to remember is just the ratio, R, the definition of R. Now going back to the slides. So sometimes you're not applying your stress like a sine wave. Sometimes you apply like square or triangular wave or even random lights, but doesn't matter. But most of the time for engineering, we tend to use the sine wave. That's easy to apply. And if you're talking about cyclic fatigue test, so that's something we can do. For example, this one, this is the most standard one, R equal to minus 1, okay? This basically mean stress is 0, and you shift up and shift down. I don't know why this is equal to 0.1, seems wrong. If you think about minimum over that value, should be wrong here, okay? And so basically this is a typical example for doing this fatigue test, which is push and pull for 1,000 times. And this is a dog bone sample. And you can also do that like a bending test, so that you apply uniaxial, basically is a concentrated force at the tip of this cantilever. And you generate bending stress, but in the end, it generates tensile stress at the top, compressive stress at the bottom. So basically, again, like the push and the pull. Okay? And there's one test I just found a video from YouTube you can watch. Basically, it's a 3-point bending on a T-shaped beam. So the cross-section is a T-shape. So let's just look at the video. So now you can find actually this the top pin, which is this one, and 2 bottom pin around here. And the sample is the T-shape. This is the top line, and this is the one in this part, voltage part. And you will see actually there's a crack going through. So let's just watch this fatigue crack. Obviously, they kind of accelerate the time. Otherwise, it takes several hours to watch that, or several days. So a crack has already initiated, but you couldn't see that. That's the bending force. The fatigue test was run at 30 hertz with a 20 kilohertz load. And 15 minutes later, okay, they compressed the video to show the crack initiation. You can see the vibration. That's basically you apply that load very quick. So microscopic crack could happen much earlier. Now you can see a crack. So each load cycle causes a small amount of crack rolls. Okay. This is quite like brittle failure because it suddenly goes through very long. I can feel the screen is shaking. I don't know. Okay, almost reached the final failure. So you will eventually see the sample is fully fractured. That's a very tiny amount of, now that's the final failure. So that gives you this feeling of what fatigue failure looks like, okay? So typically how we do the test and how we record the data is we plot that in stress over or against the number of cycle, like this. So we call it stress cycle number curve. So basically, if you look at this one, if you apply a stress very high, like that's the stress amplitude, basically half of your sine wave. If you apply that stress very high, then basically reach the yield strength of the material, it will end up no cycle number. It just fail very early. But if you reduce the stress amplitude towards this side, then you actually just apply like a tiny amount of load, and you're trying to fail the sample, but it takes much longer, sometimes like 10 to 6. Okay, that's a long time. And so most of the time, if we do the experiment, we will choose the first specimen around the stress just below the yield strength, somewhere here, so that we can see some cycle number, but not failure so quick. And we can reduce the stress amplitude like half, and do another test. Now you have a much longer cycle life, and you get another point. So roughly it takes a lot of time to plot this curve because each data point takes time. Okay? But there's some special point above here, where you apply like 10% of the load, and they are actually the survivors. Basically, the sample will never fail. It just means they will keep there no matter how longer you increase the cycle life. I mean cycle loading. So it didn't fail. So that is called the fatigue limit for a material. So basically, fatigue limit is the stress, the quantification of the stress. If you look at this one, so normally we look at the stress when R equal to -1, that's mean stress equal to 0. So give you this fatigue limit here, where if you're below that stress, the material will never fail. Okay, fatigue limit is defined in that curve. So if you look at most of the engineering material like ferrous alloy or titanium alloy, they all show fatigue limit when the fatigue stress is about less than 30% of the ultimate failure strength. Okay, except aluminium seems. Okay, and so if there's no fatigue limit, basically means it will eventually fail no matter how small stress you apply. So then mostly you read this final value as your fatigue strength. For example, that's the fatigue strength which give you the number of cycles 10 to 7. So you cut a line here that say, okay, that's long enough. Let's just define that is my fatigue strength. So at that point, the material will fail. But below that point, still, the material will not fail. But most of the time, you need to give a material a fatigue strength for engineering design. So you just cut a line. We need some stimulation. Otherwise, we also get fatigued. Okay? Okay, this is a very important concept. Whenever a market read, so you need to actually look at when you want to revise this lecture. So low and high cycle fatigue. Low means it will fail very early. There's a limited amount of fatigue cycle. And when that happens, because you apply stress exceed the yield strength, sigma over sigma yield. However, for the high cycle fatigue, basically this one is much smaller than that, sigma y. Okay? And so most of the time for the low cycle fatigue is because you have reached the yielding point, you generate some plastic deformation for the material, and the material will fail very quick. So this type of number will be relatively small. And people will using different measures for that, but I'll give you some example for this low cyclic fatigue. For example, such as the shock loading to the suspension. For example, that rally car is flying and boom, landing on the ground. And there's some kind of a shock loading, which in some small amount of time generates very high stress. Or some wind load on a large structure, such as bridge. Okay? So in this module, we tend to focus on the high cycle fatigue, because that's the way we can design the material have a longer fatigue life. And most of the engineering material, they are running the stress much below their yield strength. So that's more meaningful to us. So yield strength, which in that small amount of yield strength will give you a fatigue life over 10 to 4 times. Okay? The number could be very high. And so give you an example for the high cycle fatigue. For example, the rotating machinery or all the bearings or railway line, some example I'm showing you. Okay? So there's some simple rules for design. There's two rules here which are both useful. They're from different angles to look at this problem. The first one is called cumulative damage rule. There's another name for it. It's minus rule. This is the name of one mechanician. So that means if the material experiences more than one stress amplitude, that doesn't mean anything, sorry. I think this sentence is not meaningful. We will look at the detail. And the Goodman relationship, okay, that's another useful one. Goodman actually give us some good example to define the fatigue. So let's look at the minus rules. So basically, is again look at the stress fatigue life curve for a specific material. And so most of the time, if you think you apply a stress, that's a defined stress like that R equal to -1. But you can also apply different stress amplitude. You increase the stress amplitude or reduce that. They're all giving you different cycle life. So, but suppose I give you a material, I ask you to do different amplitude, and I ask you how to predict the final failure life. So how to do that? So basically, each part will contribute the cyclic life, the failure of the fatigue life of the material. So basically, this minus rule is to help you to answer that questions. How to predict fatigue life if you apply different amplitude. So for example here, I have this Sn curve. If I apply stress amplitude at around here, sigma A around here, it will give you an answer here, 10 to 4. How about if I apply stress at here for a certain number, but the material haven't failed because it haven't reached this line. And I apply another stress, and it will have another type of, I just stop here at 10 to 3. Again, the material haven't failed. But in real life, you need to think about both of them contribute to the final failure. So you need to think about how to predict that. So minor actually give us a good indication. So suppose here you have 10 cycles, and then your fatigue life will be 100 actually, right? So that will generate damage 10 over 100. That generate damage parameter is 0.1. That's kind of a quantification of that damage. And here, similarly, you get probably 0.2. And then you need another several type of stress. Adding up in total will give you the total damage parameter equal to 1. So what I'm saying is this is one type of stress amplitude you applied. It give you some damage. They must be smaller than 1. And this is similar, another stress amplitude. So adding different amplitude together then give you the final damage. Once it reaches 1, then there is some damage. I'm not sure you understand that well, but let me give you some example more to help you to understand what happened here. So basically, we're looking at the damage. If damage equal to 0, that's no fatigue damage. If damage equal to 1, that's full damage, completely damage. And when we're doing different stress amplitude, you generate a small amount of damage. In the end, you accumulate them together until they reach to 1. Okay? So let's look at an example here. So here is an example showing you the Sn curve. So I want to pick my pen again to showing you how I approach these questions. So you have this stress, this number. So that's called SN curve. Okay, SN curve. So now, first of all, I apply a stress at amplitude sigma A1. So if you can look at the slide as well, I point that stress A1 around here. Okay. However, I stop to run so many cycles. I just stop in the middle somewhere here. Okay, and let's put an arrow here. We stop here. So that already generates some small amount of damage on the material. And at about here is 10 to 4. Okay? And I tell you the number I cycled at this stress, sigma A1. So the number I cycled, N1, is 5 times 10 to 4. That's 5, okay? 5 times 10 to 4. Again, and I take that sample out, and I try to apply another stress, which is sigma A2 around here. Now, I'm not to fail the sample. I'm not reach that SN curve. I stop somewhere here. So let's put a dot here, sigma here. But eventually, if you draw the dashed line, it will fail at that point. So N2, I apply how many cycles here? N2 is 5 times 10 to 3, 5,000 cycle. And I take it again, take that up again. And number 3, I apply a stress A3. So this dashed line go here, and I stop somewhere here. I draw arrow here. N3 equal to 2 times 10 to 5. Okay, I stop here. And the question is asking, if you apply stress at sigma A4, when the material will fail? So sigma, well, I'm asking you the number of N4. So N4 you can read. I don't know where I should stop. So for most of these things, the number you stop is here, is telling you, okay? But the actual failure number for the sigma A1, which we put here, NF1, is 10 to 7. And sigma A3, if you go to here, I should use another color, sorry. So this just forget some of the dashed line. It may get you confused. So this is at sigma A3, you have a failure cycle, a fatigue life, which is, and this one, okay, that's NF3. So if at this stress, it should fail at 10 to 5. So NF4, that's the fatigue life for each of them. Okay? Yes, that's true. So that is NF3. That is NF2. Yeah, exactly. And now I'm asking you how to get this value. So let's think about the minus rule, which is the sum of all the damage from each part. So Ni over the fatigue life of that specific load equal to 1. So let's expand this equation. So N1 over Nf1. So basically this part plus N2 Nf2 failure life, N3 Nf3 N4 over Nf4. This should equal to 1. So now actually you know this part, this part, this part, but you don't know this one. So it's basically a very easy math problem. You just need to substitute all the value for the other term, and then you get this one. So let's plug in the value in. For this one, 5 times 10 to 4. If you read this fatigue life, that's 10 to 7. Plus, N2 is around here. I just stop the load cycle at 5,000. But if I look at the failure life, is 10 to 4. Similarly for this one. Can you see that? Okay. It's a bit too zoomed in. So sigma 3, this line, I stop around 2 times 10 to 5. But if you look at the fatigue life, it's 10 to 6. So plus this unknown, okay? I know fatigue life for NF4, which is 10 to minus 5, equal to 1, okay? So in the end, I got 10 to minus over 10 is 1 minus all the term here, bracket term, which give you, I will give you the answer directly, okay? So if my drawing here is not clear to understand, you can look at the slides, so which is essentially the same. So N4, this N4 over the NF4 will equal to 0.259. And the final answer for the total number you should apply to reach the failure is 2.95 10 to 4 cycles. Okay? So you should stop about here. 2. Okay? You should stop up around here. That's the answer, okay? Okay? Let me see how much we go. Okay, let's just finish the minus rule. Okay, minus rule basically is a cumulative damage rule. So I think that example helps you to understand how we use the equation. Any question? Yeah. That's an approximation model, I think. That's basically assumption to use a parameter to quantify the damage. So basically it's a model, but is quite useful for engineering design in this case. Okay. I think we need to go through the Goodman relation, but let me see how many slides. It's probably too much for you to have that. Do you want to have a break? Okay, have a break and come back 10 minutes. Material, if you think about it, we're applying at R equal to -1 stress ratio in this case. And we will get this curve, and most of the material will showing the fatigue limit. So the next slide, we're talking about the Goodman's relationship. It's based on assumption you have this fatigue limit for material. Otherwise, that relationship is not valid. Okay? Fatigue limit basically means upon you're reaching that point, I mean, sigma t, if you reach that limit, you still have the failure from fatigue. If you're below that stress, the failure is not initiated, will have an infinite fatigue life. So infinitely longer life. Okay. And for this case, Goodman's relation, I think it's really a good example of good relation. So why we think about that is for material showing this fatigue limit, we actually need to think about if you have different fatigue load you apply, you can change the mean stress, you can change the stress amplitude. And what happens if you can design a material which you can have an infinite long fatigue life? That would be ideal for all the engineering structure. So this relationship to help you to design that. So let's just recap you this R. We're talking about R to equal to -1. Again, just this part. We don't care the other two. So Goodman diagram basically means if you draw this curve, so look at the axis, stress amplitude here on the y-axis again. But now we change the fatigue life n to mean stress, sigma mean. So which is kind of hard to understand why we plot two stress together at different axes. Let me tell you why. So if you look at some special point, if you look at the origin here, where mean stress equal to 0, which basically for the R equal to 1, that's this line. And the whole horizontal line basically means sigma m equal to, sorry, the origin means sigma m equal to 0. Okay? That represents this type of loading you applied. So sigma mean is equal to 0. But in this case, you can see actually you can have very large stress amplitude as you want to keep your material in a safe region. So in the area below this curve, that's the safe region without any fatigue failure. But if you exceed that curve, that's the failure from fatigue. Okay? That is the first case for the origin, R equal to -1. How about for R equal to 0.1, which you get this value. Okay? R equal to -0.1, basically you shift your mean stress up around here. And if you work out R, this minimum over the maximum give you roughly 0.1. And it's very close to your ultimate tensile strength, which is this dashed line. In that case, you actually, you can see your amplitude is decreasing. Otherwise, you will easily fail the material, right? So in this case, if you still want to have a safe region, you need to reduce your stress amplitude. So eventually, you will reach that value, sigma UTS, ultimate strength, and your amplitude will equal to 0. So that is your final applied stress amplitude without any wave, basically equal to a straight line for that point. Okay? So if you look at some other case, which similarly, I already pointed out r equal to -1. If r equal to 0, what that means, r equal to 0, let me remind you, which is the value here, r equal to 0, this one. So that means the sigma mean is 0, while sigma max can be anything. So what happens, sigma r equal to 0, for that case, again, you're shifting your mean stress up from that mean stress equal to 0 to somewhere between. So r equal to 0 will give you some indication that the stress amplitude need to reduce, has to be reduced from this value to that value. And that gives you this relationship. And if you further shift your mean stress up from here to here or even to here, so r is larger than 0, which is this case, will give you the region around here. Okay? So that's how you read this curve, just to connect you with the SN curve. It's very similar, but not exactly. But the main difference is the stress is plotting in the horizontal axis. So that's what I mean, safe in this triangle region. But outside is fatigue is triggered. Okay. So Goodman relation, if you let's just derive this curve, what that means. Let's just derive that. It's not that hard. So I give you this plot. Again, plot now is sigma A, this stress amplitude, plot against the mean stress. And what you know initially is this point, which is equal to fatigue limit, sigma T. Fatigue limit. So that's why we need the Goodman relationship must have the fatigue limit for this material. Otherwise, you don't have that dot. And then you have the sigma UTS, failure strength, ultimate tensile strength. And you connect this curve, basically, this is just a line equation. So do you remember how to write this line equation in a mathematical form? So that's the question. So for a line equation, do you remember just the basic equation is y equal to kx plus b for any type of line. So any type of line like this. So k is the gradient of your line. Gradient, okay? And plus b is the cross-section here. So say here is 0b, that point. Okay? So that means if you x equal to 0, y will equal to b. So give you this point. Vice versa, if you such that y equal to 0, x will give you minus, in this case, let me see. This is 0, so it's minus b over k, okay? In this case, k is the negative sign. So now we're doing similar things. So let's just write this point in a form like 0 sigma t. You can write this as sigma UTS 0. That's the 2 points you know. So now, if you give me 2 points, that can define a line. So now we derive the equation for that. So let's work out the gradient of this curve, which is, by the definition of the gradient, you basically is the y2 minus y1, x2 over x1. That's the definition for a gradient of a line. So now we know, say this is this is the number dot A and dot B. So let's just type this dot as, so for this case, y2 for this case is 0. And y1 is for that, sigma t. For this case, the x2 for this one, UTS minus that one. So give you minus sigma t over sigma UTS, right? So that gives you the gradient of the curve. You can see it's a negative sign. That's right. Otherwise, it would give you a positive value. So B here actually is the cross-section value. It's sigma t. Now you know these two coefficients, y equal to kxb, is basically, you know y here is the axis you're plotting, sigma a. You know x here is the sigma mean you're plotting here. So using that, we know sigma a equal to this k. We replace the k by this term, sigma t over sigma UTS, times x, the variable in the horizontal axis, plus the b, sigma t. Okay, you can see that. Now, let's just rearrange the equation. So finally, what we want to get is sigma a. We just simplify this equation by taking out all the sigma t. And now you can see it's 1 minus sigma mean over sigma UTS. Let's just put a bracket here. So now you can see that's exactly the equation here. So you just derive from that line equation to get this answer. That's the Goodman relation. Okay? So not that hard. It's actually just some mathematic problem. What's happened? Okay. Yeah. Now, so I probably will ask you, probably in the coursework, there is one question to ask you to describe what the meaning of Goodman relation. So the equation should be expanded like this. But what the physical meaning? That's the question. Okay? Let's look at that. So bear in mind, we are doing that when r equal to minus 1, then you can get some of the value, sigma t. Yeah, sigma t is obtained when r equal to minus 1. Okay? So if you give me the mean stress and also your fatigue limit, I will tell you how much stress amplitude you should apply to actually have that fatigue life. Okay, so that's the engineering design. It's very easy to use. Basically, if you need any of this parameter, you can get the one unknown from the equation. Okay, so the aim is to find the infinite fatigue life. Basically, is this fatigue limit part, and just to reduce your stress amplitude. So suppose you design a bridge, and that bridge can tolerate how much maximum load. So that maximum load basically will relevant to your stress amplitude eventually, right? To have like 20 years of fatigue life. So eventually you will telling the engineer how to design and such that you have a infinite fatigue life. Okay. Now let's just do an example to help you understand this Goodman's relation. So a titanium alloy is subject to a cyclic stress amplitude. Cyclic stress amplitude of 275 megapascal. Okay, that's the first things we get. So let's just write that down. Sigma A equal to 275 megapascal. The alloy has an ultimate tensile strength. Sigma UTS equal to 930 megapascal. And the fatigue limit, sigma T, is equal to 363 megapascal. Okay? So the question is, calculate the maximum value of the mean stress such that the alloy can withstand without being fatigued and the corresponding R ratio under this condition. Okay? So basically you need to work out the mean stress, maximum mean stress, and the R ratio. That's the question. Question 1, question 2. So we have just write down these known parameters and just come back to this Goodman relationship, which is just rewrite it again. Okay, can you see it? Okay, 1 minus sigma m, sigma UTS. Someone is calling me. Okay, sorry. And what's going on? Maximum mean stress. So I'm asking how to get maximum mean stress. So all this value is kind of valid, especially this kind of fatigue limit give you the critical value. Okay. Now let's work out sigma mean. Mean stress, if you look at the equation, it's very straightforward. We know this and that. The only thing we don't know is the sigma mean. So that just a bit rearrange of the equation. So let's just do some math again. So what I tend to do is sigma A over sigma T, just divide that 1 minus sigma m, sigma UTS. Now I then rearrange these parts so such that sigma UTS equal to 1 minus sigma A, sigma T. So eventually you times this over, give you sigma UTS, put a bracket 1 over sigma A, sigma T. Right? Just rearranging the equation. And that gives you the answer. You plug in all the value. That gives you the answer, which is 225.5 megapascal. And the question 2, which is about the stress ratio R. If you look at the R definition, which is the sigma mean over sigma max. So now we don't know what the value for sigma mean and sigma max. So how to get that? So if you look at the curve, there's some hiding relationship you probably forget. If you just look at one of the cycle curve at the beginning. Okay, or the plot, I have plot here. Okay? That's the variables I define here. Okay? But there's a two more relationship you can find actually from here, which you can find sigma mean if it's the middle value, and sigma max actually is the sigma mean plus sigma amplitude, right? So you will get sigma max equal to sigma mean plus sigma A, right? Just you know the amplitude, and now you know the mean stress that give you the sigma max. Similarly, sigma minimum is a sigma mean minus sigma A. Okay, put a comma here. So that's the relationship you can also find. So now going back to these questions. So basically you put that back. Sigma mean minus sigma A. Sigma mean plus sigma A. Okay. So that's the final answer for this. So just be careful of the calculation. So now you get like 225.5 minus sigma A is 275. And this is the plus. So that gives you the minus 0.10. Okay? So that's the answer for these questions. So Goodman relationship basically to help you to find, I said, use the fatigue limit to find where you apply the stress amplitude or apply the stress, the mean stress, such that you have an infinite fatigue life. So point to remember for all of these I have said. So fatigue test for cyclic loading test, that's some example of fatigue test. And most importantly, to remember this SN curve, and also the definition of low cycle and high cycle fatigue conditions, and explain the physical meaning for that. And the Miner's rules and the Goodman's relation. So that's basically end this story. We are talking about using the stress as a measure to quantify the fatigue life. But eventually, you will trigger some crack. The crack will initiate and will propagate. So basically, now we are going to this kind of fracture problem. So just like before, we first of all talking about the yield stress, and then we talk about the fracture mechanics. Then now similarly, we talk about the stress for fatigue, and we are talking about the probably stress intensity factor for the fatigue. And we are talking about the fatigue cracks. Okay? So eventually you can see there's a crack happens for a single crystal copper. This is an example. And we need to know what's the origin or the mechanism for this fatigue growth. What's happened in the micro scale. That's very important. So here, I highlight here is due to dislocations for the metallic material. So let's look at what's happened in the micro scale. So in the micro scale, if you look at metal, you can think about is a crystal, a polycrystal material. So one of these kind of hexagonal shape is the crystal, and they are having this crystal grain boundary. This green boundary is the weak place. And this is the single crystal, but if you look at here, the left-hand side is the material surface. So whenever I look at the microstructure of the material, I tend to polish the surface. Most of the time, you will look at here, from the optical microscope, you can look at the cross-section. Just from the left-hand side view, you can see the surface, whether it's smooth or not. But most of the time, actually, the material have some surface flaw or initial kind of imperfections, such as kind of things I draw here. So this can can be a trigger for this fatigue crack growth initiation, first of all. So what happens for that? So for this kind of imperfection, you can have dense scratches, you can have some corrosion bit, you can have some intrusion or extrusion, and also some geometric shape changes. So under fatigue stress, you load a tension or compression several hundred cycles, actually you will trigger some dislocations, something like that. So basically each of these strips represent that slip direction. So slip will happen along that line. So just ask you, so everyone know the dislocations or not? How many of you know the dislocations? Not everyone seems actually. So probably most people, most students, if you're from material science background, you probably know a lot of dislocations because of the material. Mostly you are doing is metallic material. So dislocation is the concept for the kind of for a crystal like that. It's basically generate some, in micro scale, it's like generate some shear stress such that your crystal can glide along that plane. So like what I'm drawing here. So there's a lot of slip happens. Slip is the moment or the motion of dislocation. Dislocation, basically you dislocate at the atom in atom level, but in micro scale level, you will see the crystal will have this slip band like that. Okay? So it will generate some, you can see the surface which looks like that, which we call it intrusion or extrusion. Some of them are pushed inside and some of them are extrude out, like this shape. So eventually, probably, like I said, there is a slip plane which you have the maximum resolved shear stress. So think about the Triskar shear criteria. Basically, you introduce like a 45-degree angle where here has the maximum shear stress to force the material to have the slip or dislocation failure. And if you look at the microstructure surface, you will see these things. So let's just look at the experiment, how it looks like. Okay? Sometimes the environmental, like oxidation or corrosion, will also help that happens much quicker. Okay? So we are talking about stage one. When you have the slip happens, eventually you will have the maximum stress on one of these slip planes, and it will trigger the crack, and it will follow that crack and go into here. So what I said is mode 2 failure on this kind of in microstructure. So let's look at what happens. This is again a simplification of what I've drawn before. You will end up have this intrusion and extrusion failure on the surface of the crack. But if you look at the SEM image, you will see what happens for that. If you just look at the surface of the material, this surface is corresponding to the left-hand side image, like this. And this is for a steel material. Okay? So you actually say this is some small irreversible plastic deformation like that occurred. Plastic deformation basically like a matrix shearing on that small scale. So on this parallel slip band, and eventually you will accumulate this extrusion like that, or intrusion inside on the surface. So if you look at some typical failure of a fracture surface of metal, you will see actually now we are looking at the material from the top. From the top, you will see actually there's some like wrinkling surface like that. So we call it like a beach marking. Like if you go to some beach, you will see some sand. We have similar pattern like that. But just give you the visualized idea of this pattern. It's more like a beach marking. So let me just read this sentence. Slow fatigue crack growth characterized by the incremental lines of beach marking that shows the changing of the crack tip direction, you can see the crack is growing that way. So suppose like you load it and reload it, load it and reload it. For example, in the beach, basically the wind is blowing here and come back, blowing here and come back. Similarly, that's kind of example to relate to this pattern. Okay, so the showing the direction of the crack propagation and the crack propagation rate. If you can see some fracture surface changing very substantially, you will see actually the crack propagation is also much quicker than before. So this is another example on alloy material. You can see at the beginning, when the cycle number is 200, you didn't see too much surface crack. We are looking at from the top. And if you increase the cycle number, so the material is actually basically loaded in plane stress conditions. You can imagine that you apply stress like along that page. And then after 4,000 cycle, around 4,000 cycle, you can see this pitch marking again. So again, they are all similar problem for metal caused by the slip band formations. The micro scale failure mechanism for that is the crack are initiated by the roughening of the surface because there's some imperfection at the beginning. And eventually the crack cyclic load will cause some plus deformation, which is represented by the slip deformation. And the deformation basically is due to dislocation. If you need to expand the micro scale mechanism, you need to remember there is a word called dislocation or slip. So dislocation moments below the yield strength. So bear in mind, in this case, you are probably apply like less than 30% of your stress, yield strength on the material. But still, you have this crack initiation after several thousand cycles, and eventually it will lead into the faster fracture. And this small plastic deformation accumulate and eventually initiate a crack. So this is a very standard example you should remember. And what happens after the initiation? For example, here the slip band is initiated. There is a small micro crack initiated here, and it will actually grow to your adjacent crystal. For example, here. So, like we said in this maximum hoop stress, eventually your crack will be in a direction normal to your loading stress. So that's why it's a horizontal line here. So it will grow perpendicular to your loading axis, okay, in this direction and in a kind of zigzag manner. So eventually this crystal here will be fractured, okay? And whenever you're looking at the surface, for example here, from left view, you will see this pitch marking. Or you cut somewhere here, it will also give you some like zigzag pattern like that, okay? And eventually you will reach some point, you're reaching the critical point for the material, which is the critical stress intensity factor, where you quantify the fracture. When the KIC is reached, then you're going to this fast brittle failure mode, and then easily you break the material. Okay, so this is the maximum point when you want to determine the crack length for the faster fracture. So this will cause, if you have a crack length A here, at the beginning is A initial crack, and up to here, you will get this critical crack length, AC, which we will have some example to solve. So now let's just summarize the 3 stages of fatigue by using these 2 images. one is in a low magnification, one is a zoomed in high magnification image. So if you look at the initiation point, it's roughly here. They are the initiation at the stress concentration point. And then you will see this pattern, which is the beach marking pattern, which basically showing you the slow crack growth due to the extrusion and intrusion of slip deformation or dislocation. And eventually you will see some fast fracture when it reaches this critical value of KIC. This is basically taken from some school from a third-year project when they look at that at SEM. So now let's look at the stress life approach. It's very similar to the SN curve we saw before. But now we need to predict the crack growth rather than just look at the initiation. Okay? So that's very important. Now you need to be aware that we need to use the KIC, the K value in this kind of calculation. Now let's just look at how we describe a fatigue crack growth. Suppose you have a single edge crack panel like this. You have your initial crack AI in this length. So cyclic stress on a crack sample, such as like a CT test or double cantilever beam test, applied on this sample. And you monitoring the crack growth during the test. And you will see eventually they will reach a critical length AC, which is around here, such that you have this slow crack propagation region, but until that point you will have a fast fracture above that point. Okay? And this is the stress, delta sigma is the stress range for your fatigue stress. So basically it's the maximum stress minus the minimum stress when you're applying that fatigue stress. Okay? Looks weird, okay? So the stress intensity at the crack tip, just remind yourself, is K equal to the correction factor times the stress, remote stress, times this square root pi a. That's for the general case for a fracture of a panel. But for cyclic stress, now you need to change that stress to this delta sigma. So basically it's a range, delta sigma. And the total change of your stress intensity also will become a range. Suppose you have a material, you need to think about how far you stretch the material from the minimum to the maximum. If you reduce it, the range, also you reduce the fatigue failure. So that's why we always have a delta here. Delta K now equal to delta sigma times the square root pi a. The crack length doesn't change here. The definition here doesn't change. Only change is these two, K and sigma. Okay? So now fatigue crack growth. Okay, just showing that all of them, which again is very similar. If you see that I'm changing all the sigma by the stress intensity factor K. Okay? I think you can draw it yourself, but now let me just go through it very quickly. So now again, K mean, you have a mean stress intensity, and you have a maximum K and a minimum K, very similar. And you have the delta K, which is the range. Okay? And the Ka is the amplitude of the changing K. So again, if you look at the definition, it's very, very similar. Mean stress intensity is the half of them, and the range and amplitude, basically very straightforward. Okay? So as the crack grows, and the K will increase. Why? Because if you look at the
definition of K. K is relevant to the crack length. So crack growth means crack length is longer. So the K will increase. So the crack growth rate will also increase. That's why for most of the crack, at the beginning it's slow crack, but in the end it will have a fast crack. So for this type of curve, I'm plotting crack length against the total number of for the failure, leading to the failure. Okay? Now I'm plotting three curves. For the first curve, where delta sigma 1 is corresponding to a small crack length. And likewise, for this one, if you increase the crack length, this curve also changes, move towards the right side. Okay? Delta sigma 3. Oh, sorry, that's a wrong description. So if you look at delta sigma 1 is the maximum here, and the delta sigma 3 the minimum. That means the small stress amplitude, the longer life. That's why you have a longer life on the right side. But if you increase the range, you will fail much earlier. And this is the critical crack length, AC1, is also reduced. And if you look at the slope of that curve, it gives you the gradient of crack length, or the gradient of the crack length over the number dA over dN. So let's look at the typical curve where this is called Paris law. So just remember this guy, Paris law. He actually submits this paper like 1960, but it ended up is a very new theory for everyone. So he got rejected by many times, and eventually he submitted to some very new mechanics journal. He get published, and it turned out to be a very successful model for this fatigue, and it get a lot of citations. So let's just remember this is a very important theory for this module, Paris law. So basically, you're plotting that gradient dA over dN against the stress intensity factor. And he divides this curve into three regions. In the first region, basically, you can imagine you are changing the stress intensity factor K by a very small amount, like that. So in that case, the crack growth rate, dA over dN, at the beginning actually is very quick. For the microstructure you're thinking about is probably in the lattice spacing per cycle. It's in the micro scale. And it can grow very quick until you reach the second state, which is more like steady state. You have a constant gradient here in the second stage, up to some stage where you reach a very high delta K, and you will reach fast fracture in that region, and eventually reach that KIC, critical value. So before that is all kind of a small amount of crack, but they will still have three different stages. So let's just look at the stage 1, where you can see the length scale 2.5 nanometer per cycle. That's really tiny. So delta K approximately corresponding to the fatigue limit. So that means you apply the stress probably less than 30% of your yield strength, very small, and that will give you an infinite fatigue limit. If you look at the region here, until you reach some crack here, crack initiation point here. So I'm talking stage A on this part. Okay? And then in region 2, if you look at the scale, 20 nanometer to 50 micron per cycle, And I mean, this is the crack length, the scale of the crack length, 20 nanometer to 50 micron. At this stage is a steady state behaviors. So you have this Paris law, very famous. He actually quantified that relationship dA over dN by a power law. So power law, by meaning a power law, you kind of have a coefficient A in front, but in the function, as a function of delta K with a power index here, N. So that will quantify your fatigue life, fatigue growth rate. Okay, that's basically to predict how quick or how slow for your crack grows. So N typically from 2 to 4 for metals. And for ceramics, it can be very quick, 20 to 40. That's why ceramics probably have a much steeper line here. If you imagine ceramics will be much steep like that, and it will fail much quicker than metal. So in the region 3, you have this Kmax approaching to the critical value, and then you have a rapid crack growth. Okay? So now let's just think about how to derive a physical quantity based on this Paris law, because he just gave us this equation, but for most of the application, you don't know some of the value. And you are given probably this coefficient and this delta K, and you will probably asked to predict the critical crack length or the fatigue life. So let's just look at how to get the fatigue life for including the fast fracture in this case. So now you need to put this equation delta K equal to y delta sigma times square root pi a. And what you need to do is think about this is a differential equation. You need integrating the whole equation such that you can get the total failure life, NF, which basically integrate this equation. So let's do that together. So look at the paper here. We are given this Paris law. dA dN equal to A times delta K with a power index N. And we know delta K here equal to y delta sigma pi A. Okay? Now it becomes much complex. Let's just do it step by step. We basically need to get the fatigue life by integrating the equation from N to NF dN. Okay? But this can be converted. If you look at this equation, this can be rewrite as dN equal to dA over A times delta K with a power index, right? So what we need to do actually is just substitute that, and we change the range for the integration, which now we are do the integration on the crack length. Crack length at the beginning is AI initial. At the end is the critical point, critical crack length. Now we plug in the dN in this equation, delta Kn. Okay? So now the second step is plug in the delta K in this equation. We can take out the A at the beginning for this case first. Now you can see actually delta k is y delta sigma pi a. Put a bracket here, put a power here, dA. Now we need to take out all the constants, which is y is constant. Delta sigma is also a constant. We know that we apply that load, and pi is a constant. Only variable is the crack length. So now let's just take all the constant out, which eventually is like that, delta sigma n. And pi is n over 2 because there's square root here. Okay? That's right. That's what and there's a y n you can put it here. And eventually it's simplified as you are doing the integration on the crack length, which you can write it here. 1 over n over 2 divided by 2 because there is a square root here. Integration on crack length. Okay? AI is the initial crack length. AC is the critical crack length. Okay? We're almost there. So let's just expand this equation. Looks very complex, but just forget about the front part because this part is all constant. We just need to look at that part. Okay? Let's think about integration of, let's say I give you a integration of x. Now it's minus dx. So just look at general equation for this one. What you get is you have this 1 n over 2. I just remember that, but you need to probably remember that as well. And okay. And what happens for this one is also one minus n over 2. Is that right? Just think about that is, let me just make it simpler because even myself couldn't remember it, what's going on there. It's actually a over x a plus 1. Is that right? If you have that, yeah, this should be 1 over this one. So that if you do the derivation, you will cancel that out, and this will going back to that equation. Excellent. So I almost get confused myself. So similarly, now you look at that. So it's 1 over this term comes plus 1, and this is the correct answer. Okay? So we're doing the similar things. Now the a equal to x. So now you will see that term AIAC dA. Now give you the answer, which one over A minus 1. So be careful, this is A initial and AC. Okay, just using this equation, you will get that. So what happens? You should remember there's another term in front of it, so it should be 1 minus n over 2. So the final equation here, when you finish that, will equal to, you put that there is probably a positive or negative sign here. So here is, here there should be a negative sign here, because I switched the direction AC. It should be this one minus that term. Now, to make it correct, now I put the negative sign in the front, so that in end, you will change this term and put that in front. And write all the constant term together. In the end, this term is AI over 2 minus 1 AC n over 2 minus 1. Okay? So that's the final answer. This is the constant. And AI should be smaller than AC, such that this term, the inverse of that term, should be larger than that term. Okay? So this will give you the fatigue life before fast fracture. Okay, I think that's it. That's for today. And I think you need to go over this derivation yourself, because you will need to use that. Okay. So next class, I will give you some example to show how to actually calculate that.